Hi everyone, today I would like to talk about the basic searching technique part 1. So this is part of the advanced AI course. So what are the main components in a searching technique? First, in order to search, we must know what is the objective of our search. That means what are we going to look for? So we call this objective function or evaluation function. So in objective function, we will define either we want to maximize or we want to minimize some function of decision variable subject to a certain constraint. So a constraint can be equal or greater than or less than. Later on we will see the example. So and then we need to have a search space. So the search space range or value of decision variables that will be searched during the optimization. So that means in the search space we have a lot of solution, and this solution is created or these solutions are created based on the value of decision variables, often a calculable size in combinatorial optimization problem. Type of solution. A solution for optimization problem specifies the value of decision variables and therefore also the value of the objective function. So a feasible solution satisfies all the constraints, or in precisely we can say feasible solution satisfies all the mandatory constraints. An optimal solution is a feasible solution and provide the best objective function value. So a near optimal solution is feasible and provide a superior objective function value but not necessarily the best. So what is tractability? Some problems are intractable. As they grow large, we are unable to solve them in reasonable time. What constitutes a reasonable time? Of size n, the worst case running time is O n to the power of k for some constant k. So we can have O n squared and so forth. So polynomial time, that means for the function of O n squared, O n power of 3, O 1, O n log n. So not in polynomial time is O 2 to the power of n, O n to the power of n. So what is polynomial time algorithms? Are some problems solvable on polynomial time? Of course, many algorithms we have studied provide polynomial time solution to the. Are all problems solvable in polynomial time? The answer is no. So Turing halting problem is not solvable by any computer no matter how much time is given. So most problems that do not yield polynomial time algorithm are either optimization or decision problem. So what are optimization and decision problems? So optimization problem is one which asks what is the optimal solution to problem X. Example is 0-1 knapsack problem, fractional knapsack problem, minimum spanning tree, traveling salesman problem, time-traveling problems, and many more. So what are decision problems? A decision problem is one which the answer is yes or no. For example, does a graph G has a MST of weight less than W? So optimization problem try to find an optimal solution. A decision problem try to find the answer for yes or no. Many problems will have decision and optimization version. For example, a traveling salesman problem for optimization problem is find the Hamiltonian cycle of minimum weight. In decision problem, is there a Hamiltonian cycle of weight less than k? Some problems are decidable but intractable. As they grow large, we are unable to solve them in a reasonable time. is there a polynomial time algorithm that solves the problem? So let's have a look on continuous and combinatorial problem. Optimization problem can be continuous, that is infinite number of feasible solutions, or combinatorial, that is a finite number of feasible solutions. Continuous problem generally maximize or minimize a function of continuous variable such as 4x plus 5y, while x and y are real numbers. On the other hand, combinatorial optimization problem dealing with when x and y are integer value, that is when variables are integer value. So combinatorial optimization problem is a mathematical study of finding optimal arrangement, grouping, ordering, or selection of discrete objects, usually finite in number. This is given by Lawler 1976. So in practice, combinatorial problems are often more difficult because there is no derivative information and the surfaces are not smooth. That means there are somewhere in the solution space that the solutions are not feasible, or they are not these solutions are not connected to each other. So what are the constraints? Constraints can be classified into hard constraint, that is must be satisfied, or sometimes we call mandatory constraint, or soft constraint, it is desirable to be satisfied. So that means we are going to satisfy as much as possible all the soft constraints. So that means soft constraint can be violated if we have no option to fulfill the soft constraint. So for example, in your course schedule, a hard constraint is that no classes are overlap. But a soft constraint is that no class before 10 a.m. That means we wish that our class is not before 10 a.m. So constraint can be explicit, that is stated in the problem, or implicit, that is embedded or obviously to the problem. Let's have a look for the constraint in constraint example. Let's say traveling salesman problem. So given the coordinate of n cities, find the shortest close tour which visit each one and only once. That is exactly once. So in this example, an implicit constraint is that all cities be visited once and only once. So what are the aspects of optimization problem? Continuous or combinatorial problem? The size of problem depend on the number of decision variables, range or count of possible value of decision variable, and the search space size. So the degree of constraint determined by number of constraint, difficulty of satisfying the constraint, proportion of feasible solution to search space. So we are dealing with single or multiple objective. That means, are we solving a single objective problem, or we are solving for many objective problems? So either the problem is deterministic, that is all variables are deterministic, or stochastic, that is the objective function and or some decision variable and or some constraint are random variables. Or the problem is decomposition, decomposing a problem into a series of problems and then solve them independently. For example, in let's say in cost time tabling problem, let's say we decompose the problem into two sub-problems. First, we solve the problem of assigning cost to the time slot. When this is done, then we solve the problem of assigning cost that already scheduled to the time slot into the group. So we have two problems. Decompose the cost time tabling problem into two sub-problems. So relaxation. Okay, why we decompose the problem? because some problems are very difficult to solve in one go. So we make it more simpler by breaking the problem into sub-problem or decompose the problem into few sub-problems. So relaxation. Solve the problem beyond relaxation and then can solve it back easier. That means we relax some constraint. Some problem has many constraints. So if we try to consider all the constraints, it might be very hard to find feasible solution. So what we can do is we relax some constraint by assuming that that constraint is always satisfied. So let's have a look at the simple and hard problem. What are the simple problems? Simple problem has few decision variable, differentiable, single model, objective easy to calculate, no or lack of constraint, feasibility easy to determine, single objective, and deterministic. So what are hard problems? Hard problems have many decision variables, discontinuous or combinatorial, multimodal, objective difficult to calculate, severely constrained, feasibility difficult to determine, multiple objectives, and stochastic. So simple problem, we can use enumeration or exact methods such as differentiation or mathematical programming or branch and bound will work best. For hard problem, differentiation is not possible and enumeration and exact method such as math programming are not computationally practical. That means it will take longer time. So heuristics are preferably used. So let's have a look what are the heuristic search techniques. Direct technique, that is blind search, are not always possible because they require too much time or memory. So which technique can be effective if applied correctly on the right kind of task? So this is called heuristic. So typically it requires domain-specific information. Blind search technique use an arbitrary ordering, priority of operations. So heuristic search technique make use of domain-specific information. This is called a heuristic. A heuristic is a function when applied to a state, return a number that is an estimate of the merit of the state with respect to the goal. So we use heuristic to estimate how far our solution that we obtain from the goal solution or from the goal state. So it tells us approximately how far the state is from the goal state. Heuristic are rules to search to find optimal or near optimal solutions. For example, first in, first out, last in, first out, earliest due date first, largest processing time first, shortest distance first, and many more. So in artificial intelligence, heuristics are formalized as rules for choosing those branches in a state space that are most likely to lead to an acceptable problem solution. So what is heuristic? A rule of thumb or relatively simple solution method to guide decision making to find approximate solution. For solving complex or combinatorial optimization problem, why we use heuristic search technique? AI problem solver employs heuristic in two basic solutions. First, a problem may not have an exact solution because of inherent ambiguities in the problem statement or available data. Secondly, a problem may have an exact solution but the computational cost of finding it may be prohibitive. Why we use heuristic search technique? First, faster than exact optimization algorithm. simpler, and more readily understood than most exact optimization problems. However, heuristics do not in general provide optimal solution. That means when we use heuristic, there is no guarantee that we can find optimal solution or even feasible solution. So search basic. Search is the term used for constructing, improving solution to obtain the optimum or near optimum solution. So a solution is an encoding representing the solution. So the neighborhood is a nearby solution in the encoding or solution space. Move is the transforming current solution to another. Usually we call it neighboring solution. Evaluation is the solution's feasibility and the objective function value. So this will measure the quality of the obtained solution. So in order to do the search, we need to know how to do the search. That is, how to construct, how to improve the solution, and then define the solution, represent the solution in using a correct encoding scheme, define the neighborhood, define the move operator, define the evaluation function. So what is deterministic search technique? So deterministic search technique always arrive at the same final solution through the same sequence of solution, although they may depend on the initial solution. For example, is linear programming. This is a simplex method, or taboo search, simple heuristic like first in first out, last in first out, and greedy heuristic. So what are the stochastic techniques? The solution considered and their order are different depending on random variable. So that means every time we run the algorithm, we will end up with different solutions. So for example, simulated annealing, end colony optimization, genetic algorithm, and many more. So what is a local search? They find nearest optimum which may not be the real optimum. For example, is greedy heuristic. What is a global heuristic? They find the true optimum even it involves moving to worst solution during the search. What is a global search? They find the true optimum even if it involves moving to worst solution during the search. This is non-greedy approach. So what is a constructive search? Constructive search build a solution piece by piece. What is improvement? We take an initial solution and alter it to find a better solution. So these are some clarification of search technique. So let's have a look constructive heuristic. So it works by constructing a solution step by step, evaluating that solution for feasibility and value for the objective function. So it's usually a greedy or myopic, that is narrow-minded, that is they take the best thing next without regard for the rest of the solution. For example, in traveling salesman problem, the nearest city next. Take the nearest city next in constructing a tour for TS. So what is improvement heuristic? Work by constructing solution, moving to neighbor solution, evaluating that solution for feasibility and the objective function value. For example, take a tour and swap the order of two cities in the traveling salesman problem. So unfortunately, like all rules of discovery and invention, heuristics are imperfect. A heuristic is only an informed guess of the next step to take. So a heuristic can lead a search to a suboptimal solution. So or fail to find any solution at all because heuristic use limited information of the present situation. This can we can use analogy like we are in the jungle, we lost in the jungle, and we are looking for a way to go out. Sometimes we follow downhill, but we track between the mountain, for example, because we cannot see what are the way out, or the actual way out. We thought that we're going down, we will find a solution, but unfortunately, we're going down, we need to climb another mountain. Let's have a look on the example of 8 puzzle. So we want to go to this one. This is the goal state. So how are we going to move from the current or the initial solution to the goal state? So which move is the best? So let's say the empty tile. Let's say this empty tile. How to move this such that we get the goal state like this? So let's say we move the empty tile to the left. So we got this solution. If we move the empty tile to the right, we got this solution. If we move the empty tile up, we got this solution. So how are you going to tell which move is the best? So what heuristic can we use to decide which 8 puzzle move is the best or worst, considering first? So for now, we just want to establish some ordering to the possible move. So what heuristic can we use to decide which 8 puzzle move is the best, that is worst to consider first? For now, we just want to establish some ordering to the possible move. The value of the heuristic does not matter as long as it ranks the move. So later, we will worry about the actual value returned by the heuristic function. So let's say we count the number of tiles in the correct position. So the higher the number, the better. So this is easy to compute, fast, and take little memory. Probably the simplest heuristic. Probably the simplest possible heuristic. Another approach, let's count the number of tiles in the incorrect position. So this can also be considered a lower bound on the solution of move from the solution. The best move is the one with the lowest number returned by the heuristic. That is, when the number is 0, that means all the tiles are in correct position. So is this heuristic more than a heuristic? It is always correct. Is it always correct? Is this heuristic more than a heuristic, or is it always correct? So now let us decide which move is the best. Whether you want to decide left, move right, or move up the empty tiles. So if move left, how many tiles are in the correct position? Or how many tiles in how many tiles in the wrong position? So let's have a look. Number 8 is wrong. So number 8 should be at the left, but it is in the middle. And then number 7 also wrong, so we have 2. The rest are all correct. So this heuristic value is 2. Then let's say we move the empty tiles to the right. So the empty tiles is right. Then we count how many tiles in wrong position. So compare with the goal state. So you see 5 is wrong, 6 also wrong, so we got 2, 7 also wrong, we got 3, then 8, so we got 4. So the rest are all correct. So the heuristic value is 4. Similarly, if we move this up, so we got this solution, the heuristic value is 3. So now which move is the best? We can easily tell those who has heuristic value lowest is called the best move, because this will define how many tasks are not in the correct position, or how many tasks are in wrong position. So another 8 puzzle heuristic is count how far away, that is, how many tiles movement each tile is from its correct position. Sum up the count over all the tiles. So this is another estimate on the number of moves away from a solution. So now, similarly, we do the calculation. So if we move left, so we compare this solution with the goal solution. So how many moves is the best? So we look at 7. So wrong position, but the move is 1. So how about the rest? 8 also 1. The rest are correct. So the heuristic value is 2. If we move right, the empty tile we move to the right, we got this solution. So compare this one. Okay, let's have a look on this example again. But this one we count the number of heuristic value by how far the tile from the correct position. So let's start with the initial solution. We make this empty tile, we move to the left. So we got this solution. Compare the obtained solution with the goal solution. Look at 7. 7 should be at the bottom, but it is in the middle. So we count that 1. And then 8. 8 should be here, but it is one step from the actual position. So we count by 1 also. So total is 2. Then similarly, the empty tiles, we move to the right. So we got this solution. So we calculate how far this tile from the correct position compared to the goal stick. So 1, 2, 3 all correct. 8 should be here, but here is 7. So 8 is one step from the correct position, so it's 1. 6 also one position. That means 1. 7 also one position, so we got another 1, so it's 3. Then 5 also one position from the correct position, so the total is 4. Similarly, if we move the empty tiles to move up, then we got this solution. So this solution, the heuristic value also 4. So which one is the best move? So since this one calculate how far from the correct position, so the minimum value is better. So in this case, again, this is the best move. So the techniques. There are a variety of such techniques that rely on the estimate value provided by heuristic function. In all cases, the quality of solution obtained by the heuristic is important in real-life application of the technique. So that means in practical, the heuristic value or the quality of the solution is more important than the algorithm itself or the heuristic. Thank you very much for listening. You can send me email if you want to inquiry any. You may contact me if you have any question regarding this.